derive it. Now, I just want to warn you, this is very, very important. I've been telling you that the quantum Fourier transform in my definition, right? And also many people's definition, not only mine, but I need to make is this, right? The quantum Fourier transform, you see that the matrix is 1 over square root n with omega to the power negative kj, kth row, jth column. And last time I showed you that the inverse quantum Fourier transform is exactly the same because they are Hermitian and also, they're not Hermitian, they are unitary, and it also is the same as its inverse. It is just omega kj. This is my definition. And why I define this way? Because this is the same as the discrete Fourier transform. So that makes sense. I try to define, say, this matrix is the quantum Fourier transform. But there are other definitions that I just call it new or other, right? There are other definitions. The inverse quantum Fourier transform, I call it new or others, right? Which very common also, maybe even more common than mine, right? Unfortunately, is the same as our quantum Fourier transform. Okay, which means it has this form. Omega to the power negative kj. Okay, so what I call quantum Fourier transform, some people might call it inverse quantum Fourier transform. I think in Qiskit, that is what they do. And then when you look at an algorithm, my textbook might say that I'm doing quantum Fourier transform for this. But you find that in Qiskit, they say it is called inverse quantum Fourier transform. So it's just a naming issue. Okay, so you need to be very careful if you go to this level, right? When people say they have a quantum Fourier transform, confirm with them which matrix you are talking about, right? Everything else the same except just the negative sign. So similarly, because it's unitary and inverse equal to the it's unitary, inverse equal to the equal to adjoint matrix. The quantum Fourier transform, right? You can call it new or others, whatever, is equal to my inverse quantum Fourier transform, which is 1 over square root n omega kj. Okay. Again, I say mine, it's not mine. Many people use what I'm doing also because I learned from those sources also. It's not I invented that, right? Now then why? What is the real difference, right, among this? The only difference is just plus minus. But what is the meaning of this? In my case, when we use negative kj, I'm not going to prove it. You can take a look in my textbook. But basically, when you apply this quantum Fourier transform, right, U, Q, F, T, you actually rotate the coordinate. Okay, so for example, I have a vector which is V. I have the original coordinate which is 0 and 1. You apply this quantum Fourier transform, you're actually rotating the coordinate to the red one. Rotate it clockwise. But the new one or others, it rotates the vector. Okay, you apply that one, you actually rotate it from V to V new. And they're equivalent. Not equivalent. I mean, they have the, equivalent in the sense with respect to the basis, right? Because now the distance between the vector originally was so much. After you rotate it becomes this. Now I rotate this vector, it becomes this. They're the same, right? But the main point here is that I just want to explain why there are two definitions. This quantum Fourier transform with negative is because I call it quantum Fourier transform because it's just discrete Fourier transform, the same matrix. So I call it quantum Fourier transform. But people use this negative version as inverse quantum Fourier transform, or the positive version as the quantum Fourier transform, is because it defines how it rotates the basis vector. Remember, I've been saying that all the gates are based on the definition of how it rotates the vector, right? So this is more consistent with the traditional definition of what a gate is. Okay, so that's all I want to say. But so in summary, remember, quantum Fourier transform and inverse quantum Fourier transform are the same, except they have different sign. One is minus, one is plus. In this class, negative is always quantum Fourier transform, right? But you read other tests, be careful what they are talking about. Okay? Any questions? Does it mean what? Hermitian? It's not equal to inverse. QFT is not equal to the inverse of QFT, right? Because one is minus, one is plus. Here you're saying that another definition. So someone called the inverse quantum Fourier transform, it is the same as our definition. Yeah. So if you, in this class, all of us say in this class, you can ignore this line. Just follow all my definition. But if later you see someone saying something opposite to mine, right? Their quantum Fourier transform looks like it's my inverse quantum Fourier transform. Come back to this line, because we just have different naming system. That's it. Okay? Yeah. No, we don't perform discrete Fourier transform. We just say that we first understand what was the discrete Fourier transform, and I just tell you that quantum Fourier transform has the same form as the discrete Fourier transform. And use that also have an insight that it try to transform one basis to mix up the basis, right? That's it. But we don't do discrete Fourier transform in quantum computer.